Welcome back to the deep dive. Today, we're really going under the hood. We're moving past the surface of digital security and getting into the heavy, almost beautiful mathematics that makes the whole engine run.
That's right. We're not talking about keys and locks in a physical sense. We're talking about numbers.
Yeah.
Numbers so mind-bogglingly large that they literally define the border between what's possible to compute and what is just completely impossible.
Yeah, and our goal today is to build that foundation, really understand it from the ground up. We're looking at the number theory that makes public key cryptography, specifically RSA, actually work. So our mission is to lay down that theoretical bedrock piece by piece. Also, sources are just full of these theorems and definitions, so we're going to try and get expert translators for you.
Right.
We're looking at four, I'd say, powerhouse ideas. First, how do we even calculate with these giant numbers efficiently? Then how do we count the numbers that are, actually usable for cryptography?
The important ones.
Exactly. Then, what's the mathematical trick that guarantees you can always get your original message back?
Yeah.
And finally, how do we even find the prime numbers we need to build this whole thing in the first place?
And look, I know this sounds complex. It is complex material. But our goal here is absolute accessibility. We're going to break it all down with some, I think, really clear analogies. We want to give you those aha moments without that feeling of just being buried in equations.
Because at the end of the day, this entire deep dive, all this theory, it really just boils down to one simple need.
Efficiency.
Efficiency. You're dealing with numbers that have hundreds, sometimes thousands of digits. You just can't brute force it. You need mathematical power tools, you need shortcuts, and you need guarantees that are just ironclad.
Absolutely. And the very first tool we're going to pull out of the toolbox is designed for exactly that, for making these colossal calculations manageable.
Okay, so let's start there. The Chinese remainder theorem, CRT. The core problem, as our sources lay it out, seems pretty simple on its face. If you have a massive number, let's call it M.
Yeah, a huge one, maybe 2048 bits.
Right? Doing math in that world, in what mathematicians call a large ring, is just painfully slow. It eats up resources.
Think of it like this. Imagine you have a single gigantic maze, and it's miles and miles long. You could have one person start at the beginning and just walk the whole thing. It would take forever.
Sure.
The CRT is a different strategy. It asks, what if you could split that one huge maze into, say, 10 smaller, totally separate mazes? You put 10 people on it, they all solve their little piece at the same time.
And then you somehow stitch their answers together at the end.
And you stitch them together flawlessly to get the one single solution for the big maze. That's it. That's mathematical parallel processing.
So for a cryptographer, the motivation is obvious. Instead of doing one huge slow calculation, you do a bunch of small, fast calculations at the same time. But that raises a huge question for me.
I think I know what it is.
When you split the problem up like that, don't you risk losing information? How do you know the answer you stitched together is the right answer?
That is the essential question. It's the mathematical guarantee we absolutely have to have. And to prove it, we have to talk a little bit about algebraic structures. We need to be certain that the big number world, the big ring, is mathematically the same as the collection of all the small number worlds.
What does the same mean here mathematically?
So we start with a concept called a homomorphism. It's basically a structure-preserving map. A translation.
Like,
it means if you take two numbers in your big world, say A and B, and you multiply them together, and then you translate that result into the small worlds, you get the exact same answer as if you translated A and B first and then multiplied them in their little worlds.
so the order of operations doesn't matter. Multiply then map, or map then multiply. The structure of the math holds up.
Precisely. But for our purpose, we need something even stronger. We don't just want the structure to hold up. We want them to be mathematical twins.
And that's an isomorphism.
That's an isomorphism. It's a homomorphism that's also, well, it's bijective. A perfect two-way street. Every single number in the big world maps to one and only one unique combination in the small worlds. And every possible combination in the small worlds maps back to exactly one number in the big one.
A perfect one-to-one correspondence. No ambiguity. No lost information.
If they're isomorphic, they are, for all intents and purposes, structurally identical, indistinguishable.
So the CRT provides the translation mechanism. It says take a number x from the big world and you map it to a vector, a list of its remainders in each of the smaller worlds.
Right. X mod M1, X mod M2, and so on. And that mapping is always a homomorphism. The math always works.
But the killer feature, The thing that makes it an isomorphism is the real centerpiece of the whole theorem. This is where it gets really interesting. When does that perfect information-preserving link actually hold?
The Chinese remainder theorem gives us one simple, strict, and beautiful rule. The isomorphism holds if and only if the moduli of the small worlds, the m's, are pairwise coprime.
Meaning any two of them can't share a common factor other than one.
That's the only condition. If you meet that condition, you have a perfect equivalence. You lose zero information.
Okay, I have to poke at that. Why? Why is coprimality the magic ingredient? What goes wrong if they, say, share a factor?
That's a fantastic question because breaking the rule shows you exactly why it's there. Let's try to violate it. Let's say we want to do math modulo m equals 4.
Okay, so the numbers in that world are 0, 1, 2, and 3. 4 elements total.
Now let's try to split it into two smaller worlds. Let's pick m1 equals 2 and meter 2 equals 2. Obviously, 2 and 2 are not coprime. They share a factor of 2.
Right.
The product space, the collection of small worlds, would be pairs of remainders, a remainder mod 2 and another remainder mod 2. So the possible pairs are 0, 0, 0, 0, 1, 1, 0, and 11.
Still 4 possible outcomes. The size matches. So what's the problem?
The problem is the mapping. It's not 1-to-1 anymore. Let's try it. Let's map the numbers from our big world mod 4. X equals 0. The remainders are 0 mod 2, 0 mod 2. That's the pair. 0. Easy. X equals 1 maps to 1 mod 2, 1 mod 2. So that's 1 mod 1.
Still looks good.
Now X equals 2. What's 2 mod 2?
0. So 0 mod 2, 0 mod 2. That's 0, 0.
There it is.
We have a collision. The number 0 and the number 2 both map to the exact same pair, 0, 0.
Exactly. And you can guess what happens with X3. It maps to 11, 1, just like X-1 did. We've lost information. The whole thing has collapsed. If your parallel calculation gave you the answer, 0, 0, you'd have no idea if the real answer was 0 or 2.
The mapping isn't reversible. The structure completely failed, all because the moduli weren't coprime.
It proves that the rule is absolutely non-negotiable. It's the guarantee that you can always stitch the pieces back together and get one unique answer.
And that stitching process, that's the classical CRT problem, right? This goes way back.
Oh, way back. We're talking nearly 2,000 years. The problem of finding a number that leaves specific remainders when divided by different numbers. It shows up in ancient Chinese mathematical texts. They used it for things like counting soldiers in an army by having them line up in different formations.
That's amazing. So for cartographers, the guarantee is, as long as your small moduli are coprime, a unique solution exists. You can reliably go from the big problem to the small ones and then back again.
And we can walk through that reconstruction algorithm because this is the part that does the actual work of putting the puzzle back together. Yeah. Let's take an example. Find a number x where, let's see, x is 1 mod 3, 3 mod 4, and 2 mod 5.
Okay, multiple conditions. First step is easy, right?
Yeah.
Calculate the big modulus, m.
Yep, m is just the product. 3 times 4 times 5 is 60. Our unique answer will be somewhere between 0 and 59.
Step 2 in the source is calculating these helper numbers.
Right, m prime I. These are clever. For each modulus, its helper number is the product of all the other moduli.
So for our mod 3 world, the helper is 4 times 5, which is 20. For mod 4, it's 3 times 5, which is 15. And for mod 5, it's 3 times 4, which is 12.
Now think about why that's so clever. Take the first helper, 20. What is 20 mod 4?
It's 0.
And 20 mod 5?
Also 0.
Exactly. The helper number 20 has been designed to be 0 in every small world except its own. It only has a non-zero value in the mod 3 world. It isolates the problem.
But it doesn't leave a remainder of 1, which is what we ultimately want. 20 mod 3 is 2.
Correct. So we need to scale it. And that's step 3, finding the modular inverses. We need a scaling factor, let's call it C, for each helper number, so that when we multiply them together, the result is exactly 1 in its own little world.
So for the first one, we need 20 times C1 to be 1 mod 3. Since 20 is 2 mod 3, we need 2 times C1 to be 1 mod 3, a little trial and error, and you see C1 must be 2.
Perfect. For the next one, 15 times C2 equals 1 mod 4. Well, 15 is the same as mod equals 1 mod 4, so mod equals 1 times C2 is 1. C2 must be mod equals 1 or 3.
And the last one, 12 times C3 is 1 mod 5. 12 is 2 mod 5. We need 2 times C3 to be 1 mod 5, so C3 has to be 3.
Now we have all the pieces. Step 4 is to assemble the solution. For each of our 3 worlds, we take its special component, helper number, times its inverse times, the remainder we actually wanted.
Okay, so the first term is 20 times 2 times our desired remainder, which was 1. That's 40.
The second term is 15 times 3 times our desired remainder, which was 3. That's a 135.
And the third is 12 times 3 times our desired remainder of 2. That's 72.
Now you just add them up. 40 plus 135 plus 72 equals 247.
And the final step, step 5, is to bring that number back into our big world, We take 247 modulo 60.
which gives you 7. And if you check it, 7 mod 3 is 1, 7 mod 4 is 3, 7 mod 5 is 2. It works perfectly. It's the unique solution.
That's really elegant. Each of those terms, the 40, the 135, the 72, is like a specialist. It solves one piece of the puzzle while being completely invisible to the others.
And that functional decomposition is exactly why CRT is so critical for things like RSA. When you have to do a massive decryption or signing operation, you can use CRT to break it down, run the pieces in parallel, and get a huge speed up. It's the blueprint for efficiency.
Okay, so we know how to structure the calculation.
Yeah.
But that brings us to the next big question. Once we're inside these number worlds, what are the numbers we can actually work with? I mean, encryption has to be reversible. You have to be able to get back to where you started, which implies you need numbers that have, like, a mathematical opposite.
Exactly. In modular arithmetic, in a ring ZNZ, to be useful for a key, a number has to have a multiplicative inverse. If you encrypt with a number E, you absolutely must have a number D where E times D gets you back to 1.
And if you pick a number that doesn't have an inverse,
Your message is gone forever. It's mathematically locked. There's no way back. The elements that do have inverses, the useful ones, are called units.
which brings us directly to Euler's phi function.
Yes. The phi function, written in the n, is simply a counter. It answers a question: how many of these units are there? How many useful invertible numbers exist in the world of ZNZ?
And it turns out a number has an inverse if and only if it's coprime to the modulus, n.
That's the crucial link. So error n is just counting how many positive integers less than n don't share any factors with n.
Let's take an easy one, like AT10.
Yeah.
The numbers that aren't coprime are the ones that share a factor with 10. So anything divisible by 2 or 5.
Right. So you're left with 1, 3, 7, and 9. 4 numbers. A10 is 4. Only those 4 are safe to use as a key in that system.
And if n is a prime number, say 17, it's even easier.
Trivial, really. A prime number has no factors other than 1 in itself. So every single number smaller than it is automatically coprime to it. So for any prime, AP is just P1.
Now, in RSA, we're not using primes directly as our modulus.
Yeah.
We build a big composite number, n, by multiplying two huge primes, P and Q.
Right, N and PQ.
So we need to calculate an n, and we obviously can't just sit there and count them. We need a formula.
We do, and we build it up. First, we need a formula for prime powers, like P raised to some exponent E.
Okay.
The logic is pretty simple. To find A, you take all the numbers up to P, and you just subtract the ones that aren't coprime.
And the only numbers that aren't coprime to a power of P are the multiples of P itself.
Exactly. And how many multiples of P are there up to P? There are exactly P to the power of E1.
So the formula is just PPE1?
It's a fantastic shortcut for something like 1024, which is 1022. You don't have to check 1,000 numbers. You just do 21029. That's 324 minus 512, which is 512. Done.
So now we can connect this back to our first topic, the Chinese remainder theorem. How does that help us calculate for a general composite number like our RSA modulus n?
This is where it all ties together beautifully. That isomorphism we proved with CRT. It guarantees that the group of units in the big ring is structurally identical to the product of the groups of units in the small rings.
Which means the size of the big group of units must be the product of the sizes of the small groups.
Which means the phi function is multiplicative. If your moduli M1 and M2 are coprime, then M1 mitter 2 is just a M1 times M2.
And for RSA, our modulus is n, p, q, and since p and q are different prime numbers, they are definitely coprime.
Absolutely. So OAN is simply EP times AG.
And we know P is P1 and O key is Q1.
Which gives us the fundamental formula at the heart of RSA's key generation. The number of usable keys A is equal to P1 Q1.
And this is an incredibly important number, not just for doing the math, but for the security of the whole system.
It's the secret key. Because notice, if an attacker somehow learns the original prime factors, P and Q, they can calculate A in a heartbeat.
And if they know n, they can break the whole thing wide open. This is why the entire security of RSA boils down to one simple fact. It's easy to multiply two primes together, but it's computationally impossible to take their giant product n and factor it back into P and Q.
If factoring were easy, calculating A would be trivial, and the system would be worthless. The phi function is both the heart of its strength and the single point of its vulnerability.
Okay, so we've mapped out the geography of our number space. We know how to split the work with CRT, and we know how to count the number of useful elements with decode n. Now we get to the real magic, the identity that actually makes public and private keys work.
Right. We need a predictable, repeatable property that allows us to encrypt and then decrypt. We need to raise a message to some huge power E, get some scrambled text, and then have a way to raise that scrambled text to another power D and reliably get the original message back.
It has to be a perfect cycle.
It does. And to understand that cycle, we first need to define what's called the order of an element. If you take one of our useful invertible numbers, x, and you start multiplying it by itself, like, x by 2 by 3, you're not going to go on forever. Eventually, you have to cycle back to 1.
Right.
The smallest positive exponent k that gets you back to 1, so xk equals 1, that k is the order of x. It's the length of the cycle generated by that specific number.
We saw that with Z10Z. The number 3 had an order of 4. It went 3, 9, 7, 1, and then it would repeat. But 9 had an order of 2. It just went 9, 1, 9, 1.
Exactly. And this leads to one of the most fundamental theorems in all of group theory, Lagrange's theorem.
Okay.
It says that the order of any element in a group, that's our cycle length k, must always be an exact divisor of the total size of the group.
So in our Z10Z example, the group size was 10, which is 4, and the orders we saw were 2 and 4. Both of those divide 4.
They have to, and this has a massive consequence. If the total size of the group is an, and every element's cycle length k divides an O, what happens if you raise any element x to the power of the group size itself to n?
Well, Gauldingen has to be some multiple of k, so you're basically just going around that element's little cycle some number of times, and you'll always land back at 1.
You will always land back at 1, and that is the crucial identity. That's Euler's theorem.
The core statement. For any number x that is coprime to n, x raised to the power of n is congruent to 1 modulo n.
This is the ultimate power tool. It doesn't matter what your message x is. As long as it's one of the useful invertible ones, raising it to the n power is a universal reset button. It always takes you back to 1.
So, how does this guarantee that a private key D even exists?
Because it all revolves around the number 1. In RSA, we pick a public key, an exponent E. We need to find a private key, an exponent D, so that if you encrypt and then decrypt, you get your original message M back.
The math is you take m to the e, and then you take that whole thing to the d. So you get m to the power of e times d, and that has to equal m.
Exactly. We need m to equal m. For that to happen, the exponent e times d has to behave like the number 1, but not in normal arithmetic, in the arithmetic of the exponents.
And the exponents operate on a cycle of length.
So we don't need e to equal 1. We need e times d to be congruent to 1 modulo n z.
So finding the private key D is really just solving the equation ED equals 1 in the world of Z and Z.
You're finding the multiplicative inverse of E modulo n, and Euler's theorem is what guarantees that this inverse D will exist as long as we choose our public key E to be coprime to M.
And once you have E and N, finding D is a solved problem. You just use the extended Euclidean algorithm and it spits out the answer.
It's computationally fast, which again shows why AN is the ultimate secret. If an attacker knows n, they're stuck. But if they can factor n to get p and q, they can calculate n, run the algorithm, and find your private key D. The entire security model rests on keeping n a secret.
Now, Euler's theorem has a more famous but less general little brother.
It does. Fermat's little theorem.
Which states that if p is a prime number, then for any x, x to the power of p1 is congruent to 1 mod p.
It's just a special case of Euler's theorem. It's what you get when you apply Euler's theorem to a prime modulus. We already know that for a prime p is exactly p1, so the formula is identical.
But the distinction is important. We need the full power of Euler's theorem for our final RSA modulus n, which is composite.
Right.
But we use the simpler case, Fermat's little theorem, to help us find the building blocks, the prime numbers p and q, in the first place.
Precisely. It becomes a tool for testing primality.
Okay, so this brings us to the really practical application. We have all this amazing theory, but cryptography needs huge prime numbers. I mean, hundreds of digits long. How on earth do you find them?
Yeah, you can't just look them up in a book. And you can't use trial division, trying to divide a number n by every number up to its square root. For a 2048-bit number, that would literally take longer than the age of the universe. It's just not an option.
So we need a shortcut.
We do. And thankfully, primes aren't ridiculously rare. There's something called the prime number theorem, which gives us a good estimate. It says that for a number n, about 1 in the natural log of n numbers is prime.
So for the kind of numbers we're talking about, you might have to check, a few thousand odd numbers before you hit a prime?
So it's something like that. It's a manageable search space. We can't afford to just pick a huge random odd number and then test it. And our first, most basic test comes directly from Fermat's little theorem.
The logic being, if a number p is truly prime, then the identity AP1 quant mod p must be true for any a you pick.
It's a necessary condition. So that gives us a test. You pick your candidate number, p. You pick a random base, a. You calculate AP1 mod p, which you can do very quickly with a method called exponentiation by squaring.
And you get one of two outcomes.
Yeah.
Outcome 1, failure.
The result is not 1.
If that happens, with 100% certainty that your number p is composite, it's not prime. A real prime would have passed the test. So you throw it away and pick a new random number.
Right. But what about outcome 2? Success. The result is 1.
This is where it gets tricky. It's only probably a prime. It passed a necessary check, but that's not the same as a definitive proof.
So you can repeat the test. You try a different random base of A. If it passes again, your confidence goes up. You do it 100 times, and if it passes every single time, the probability of it being composite is incredibly small.
This raises a critical security question. If the test returns 1, why isn't that a guarantee? Why the word probably?
Because there are cheaters. There are these algebraic stowaways, rare composite numbers that are specifically structured to deceive the Fermat test.
These are the Carmichael numbers.
Yes. A Carmichael number is a composite number, like the smallest one, 561, which is 3 times 11 times 17. But it has the peculiar property that it satisfies the Fermat identity, AN1 equals 1 mod n, for almost every base edge you could choose. It masquerades as a prime.
And that's a huge problem. If you accidentally built your RSA key using a Carmichael number instead of a true prime, the math would be all wrong.
The entire algebraic foundation would be flawed. An attacker relies on the structure that Euler's theorem guarantees for a product of 2 primes. If the structure is actually something else, all the rules change, and it could create a fatal weakness an attacker could exploit to find the private key without ever having to factor the number.
So because these numbers exist, even though they're rare, the basic Fermat test is just not good enough for serious cryptography.
It's insufficient. You need something more robust. And in practice, what everyone uses is a more advanced probabilistic test called the Miller-Rabin test.
And what's different about that one?
It's still probabilistic, but it's much, much stronger. It checks for a deeper property of prime numbers related to square roots of 1. It's specifically designed to catch the Carmichael numbers. It asks questions that only a true prime can answer correctly.
So if a number passes the Miller-Rabin test multiple times?
The probability of it being a composite liar is so astronomically small. I mean, it's far, far less than the probability of a random hardware error on your computer flipping a bit and causing a problem. For all practical purposes, it's considered a prime and is safe to use.
So the whole process of finding our building blocks, these massive primes, it all hinges on the elegance of Euler's identity, but we need to armor that test with stronger rules to guarantee security.
Exactly. Without Euler and Fermat, we have no test at all. Without Miller-Rabin, the test we have is too weak to trust.
So let's bring this all together. We've done a deep dive into these 4 cornerstones of the theory that makes public key crypto not just possible, but reliable and efficient.
We started with the Chinese remainder theorem. That's our parallel processing blueprint. It lets us turn one monstrously slow calculation into a bunch of small, fast ones, as long as our moduli are coprime.
Then we needed to know the size of the world we were playing in. We used Euler's phi function to count the useful invertible numbers, giving us that all-important secret value, ACN P equals Q1, Q1.
After that, we unveiled the master key of the whole system, Euler's theorem, the identity AN equals 1 mod n. That's the mathematical guarantee that everything is a cycle, which proves that a unique decryption key D must exist.
And finally, we saw how a special case of that identity, Fermat's little theorem, gives us the tool for probabilistic primality testing, so we can efficiently find the giant primes we need to build the system, even if we have to use the stronger Miller-Rabin test to weed out those deceptive Carmichael numbers.
Taken together, those concepts are the ironclad guarantees. They are the unseen machinery humming away behind all of modern digital security, making it fast, reliable, and reversible.
So what's the final takeaway for you listening to this? I think it's this. When you see that little padlock icon in your browser, when you send a secure email, the entire mechanism that protects you relies on a predictable mathematical cycle. And the tools to create that cycle are ancient. The efficiency trick of parallel processing, solved nearly 2,000 years ago by Chinese mathematicians figuring out a numbers puzzle, the guarantee of the cycle itself, codified by Euler centuries ago. It's this incredible application of old, elegant, profound mathematical truth to the most modern problem we have, securing our digital lives. And that, I think, is a deep dive that really gives you something to mull over.
Indeed. We'll see you next time.